Hey, good, it's on. All right, so like you said, my name is Peter Seibel. I'm the tech lead for Twitter's engineering effectiveness group, which is what we call, I guess, developer efficiency at Facebook, developer productivity, developer tools, developer infrastructure. Anyway, we provide the tools and some of the processes that allow the rest of Twitter engineers to do their job. So focusing on mostly on the things that are used by most Twitter engineers, so not little niche tools that only a few teams need, and also things that are not super Twitter specific. So version control, CI, build systems, those are all like right in the wheelhouse of engineering effectiveness. So today I want to talk about how teams like us scale our work. So the TLDR is, as an industry, I would argue, we don't really know how to scale these kinds of teams. And as a consequence, we massively underinvest in this kind of work. I should probably be moving my thing forward here. So the title of my talk, as you can see, is let engineering effectiveness at Twitter, let 1,000 flowers bloom, then tear 999 of them out by the roots. Someone came up to me and was like, is that projects or people or what? And I'm like, well, we'll see. Mostly projects. So, oops, am I going forward? No, I'm going backwards. Sorry. All right, I'm just gonna blank out the screen here. So every software company starts with a single line of code written by the first developer and grows from there. So Twitter did, Facebook did, your company presumably did. And this talk is about what happens after that. As a lot of the talks today have suggested, and the keynotes talked about a lot, as an industry, we know how to scale up our software. We know how to build abstractions and modularize our code so that we can manage large code bases. And we know how to deploy our software so it can handle millions or even billions of users. We also know how to scale up organizations, how to put in those right layers of management that let thousands of people work together, more or less efficiently. On the other hand, I'd argue that we don't really have a good handle on how to manage that, scaling up that intersection between engineering and human organization. And that's the place where engineering effectiveness style groups work. And worse, it seems maybe we don't even understand how important that is and what the payoff to doing that well can be. And so I'm gonna walk you through a little bit of the war stories of Twitter history to suggest, at least at Twitter, we didn't figure that out until somewhat recently. So Twitter's first line of code was written by our now interim CEO, Jack Dorsey. He, interestingly, did not choose to go off with write it in OCaml, which would have been like a whole different history of things. He wrote it in Ruby, partly because he hired this guy who was a core Rails contributor. And that grew into what was probably the largest Rails app on the planet, affectionately known as the monorail. And so that was like we were like a big Ruby shop. However, we weren't all Ruby. In 2008, we acquired a 5-person company that doing some search stuff using Java. And at the time, Twitter was only 9 engineers, so 5 new engineers was bringing in a big diversity, into the ecosystem of Twitter development. So let 1,000 flowers bloom. And that was in 2008, that acquisition. 2008 was also the year that the first Scala was written at Twitter. You may know that we were a big Scala shop. And so some people were playing around with that. So we now had the main product, twitter.com, as a Rails app, search using Java, and folks experimenting with Scala. So let 1,000 flowers bloom. In 2009, someone started a repo called Science. At the time, creating a new repo for a new project was no big deal. That's just what you did. However, that repo grew up to be the main repository for Java code, which included the search code I talked about before, the ads team code, associated data science code, and while the platform group was moving more and more with these experiments with Scala, partly because Scala could be made to look more like Ruby to Ruby developers as we wanted to move off of Ruby. In Science, the ads team was going gung-ho on Java, and in fact, our now Senior Vice President of Engineering, Alex Redder, then an engineer, led the charge to convert what Scala code there was in the ads code base into Java. So we have Scala going this way, Java going that way. Meanwhile, a couple ambitious folks with some ex-Googlers tried to turn Science into a Google-style monorepo, which I guess we'll hear about later today, and build our own homegrown build system, Pants, based on Blaze. So let 1,000 flowers bloom. Finally, we arrive at 2010, the year of the Quadrennial Soccer World Cup, or football, if you will. So first, let me ask, raise your hand if you ever have seen the Fail Whale, like live, for reals. Sweet. Okay, so for those of you who don't, Fail Whale used to be the error page, the only error page on the internet with a fan club or something. It was cute, but it showed up quite a bit too often. It looked like this. Oops, sorry, looked like this. And so I will now reenact the 2010 World Cup for you in slides. It looked like this. Go! Go! So after that outstanding performance by our software, we decided, we need to do something about this, and very quickly decided that we needed to move off of the monorail onto more JVM-based service-oriented architecture. Around that same time, Marius Eriksson, now principal engineer, started working on a new RPC library, Finagle, was written in Scala, and took sort of advantage of that, of Scala's features, and soon became the standard model around which we built our servers. And we began an off-the-monorail effort. And again, this was partly figured we could make Scala look more like Ruby, so we can take all these Ruby developers who are working on the monorail and have them start writing services in Scala, and this is going to work out great. Meantime, some of the data scientists actually over in the ads, sort of unbeknownst to Alex Redder, for whom they worked, started working on a DSL for writing MapReduce jobs in Scala. It became Scalding. So soon we had three kinds of Scala at Twitter. Scala written by people who wished it was Ruby, Scala written by people who wished it was Java, and Scala written by people who wished it was Haskell. Let 1,000 flowers bloom. Okay, so despite all of this diversity, and perhaps even because of it, we made real progress on the reliability and scaling of our software. So fast forward 4 years to the next World Cup, and it is a totally different story. In the final Brazil versus Germany match, we handled 35.6 million tweets, and it was all good. I think we had a couple minor hiccups during that World Cup, but basically smooth sailing. So point being, we managed to scale our software, as other people in this room have done with theirs. So that was chapter 1, let 1,000 flowers bloom. Now, chapter 2, the garden is overrun. Around the time that we were celebrating our success with the World Cup traffic, things were coming a little bit to a head on the tools front. The science repo, as I mentioned, had grown up, but it had not grown up to be the monorepo. It had grown up to be one of two monorepi, which is not a place you want to be. The other monorepo was formed from all those Scala services that had spun out of the off the monorail effort, and they had all started as separate repos, but eventually were consolidated into a single repo called the Birdcage, basically in order to make it life easier for Finagle developers, including Marius Eriksson. So we got all the Scala code together. They could update the client, update the APIs, all the reasons you would want a monorepo. But you might ask, well, why, if you already had science, did we not move in there and make one monorepo? And some of that is just history. Some of it is, at the time, science was using this build system. We wrote pants. It didn't really know how to build Scala. The layout of the repo was inherited from Google, and it had this viewpoint about how that should be that was sort of at odds with how Scala projects built with SPT and later Maven wanted to be laid out. Perhaps some cultural animosity between the Java camp in science and the Scala camp in the Birdcage. So, but the real issue, perhaps, is that it was nobody's job. There was a team, developer productivity at the time. I wasn't there then, so I don't know how big exactly they were, but they didn't really have the resources to say, look, this is silly to have two monorepi, let's have one monorepo and make that decision stick and do the work to make it happen. So basically what we ended up with, in the meantime, to make matters worse, Finagle had taken off, so we were using that. Code and Science eventually came to use Finagle, so now we have a dependency from Science into the Birdcage. But Code in the Birdcage also took dependencies on Code and Science. So now we have two monorepi with dependencies, and eventually round-trip dependencies, and eventually round-trip dependencies. And so as you imagine, having to publish artifacts back and forth and update things became very painful. So we basically ended up in a situation in the monorepi described by the eponymous monorepi Twitter account as looking like this. So meanwhile, along the way, someone decided that actually to convert the Birdcage to pants, that seems good, moving them towards a common build system, However, somewhere along the line before that, Pants had been open sourced, but it was a little bit of one of these throw it over the wall open source situations. And so it was out in open source. Maybe nobody was using it for a while. We were still using Pants internally in science. It was kind of integrated into the repo. Then ex-Twitter people outside started using Pants in the open source and moving it forward. And so then when someone said, hey, let's move the Birdcage onto Pants, they said, well, look, the open source one has all these awesome features. Let's use that one. Sounds good. So now we have two monorepi, the same build system, but two different versions. And again, because this is just, there was no one's job. The people in the Birdcage were trying to make the best of their situation. People in science were doing their thing. And there was no one with enough horsepower to say, let's, enough people to say, let's actually fix this now before it becomes a real problem. There was also some things around, again, due to insufficient investment, neither version of Pants worked all that great, so teams had evolved their own weird Cogger-culted way, workarounds and different things. There was a script called Wash Pants that would aggressively remove all cache data to try and get things straightened out when they weren't working right. And we had started using Thrift, it was like Protobufs or whatever, as our data interchange format, and there was multiple Thrift compilers, and between Java and Scala that introduces some complexity. And again, no one to make decisions about like, let's just get this stuff straightened out now. So in all of which to say, it was a mess. So I arrived at April 2013. The full conversion of Birdcage to Pants was imminent. Like, we're not even going to tell you how to fix your Maven build because we're going to be on Pants so soon. That project completed a year and a half later. And in late 2013, then SVP of Engineering Chris Fry decided we would move all of our code into a monorepo. Sounds good. There were various battles about that. But basically we agreed, and in May 2014, he said we will definitely be in the monorepo July 11th. Unfortunately, he was gone a couple weeks later. However, the new head of engineering, Alex Redder, last seen deleting all the Scala code and ads, said, reaffirm the goal, but nonetheless, the date came and went without a monorepo. We have since gotten there. So a few months after he became head of engineering, Redder decided enough was enough, and he hired a new VP, who was my boss, Nandini Ramani, out of Oracle, to head up this new organization, Engineering Effectiveness, which would subsume the old developer productivity group and some other teams, and try and put, finally, enough resources behind all of the problems that we had to really support Twitter's engineers. She recruited me in a couple months later, and since then, working with all those teams that made up EE, we've been finishing off projects like the monorepo, getting on the same version of Pants, getting rid of Maven entirely. And now are thinking about what does it actually take to provide world-class tools and support to all of our engineers. So what happened? Like, why were we so good at scaling our software and so bad at scaling our tooling and our processes? So now, chapter 3, a digression about how you should think about engineering effectiveness. I think the big part of the problem is that we just don't know how to think about engineers' effectiveness at all. For software, we can, especially backend software, we can measure QPS or uptime or the amount of hardware we have to pay for to run it. And those are all like pretty easy to measure, and they're pretty easy to tie pretty straight down to the financials of the company, right? More hardware, bad, less hardware, good. Engineers' effectiveness or productivity, or however you want to call it, on the other hand, is very hard to measure. We don't really know what makes people productive, how one person contributes to a team. So we talk about like 10x engineers, even though the studies that even brought that notion into being mostly pointed at like 10x offices, not 10x engineers. So we don't have a good grip on this. However, I think we all agree that it is possible to affect people's effectiveness. We can certainly harm it. You've all probably experienced that. So in Twitter, the engineering effectiveness motto is quality, speed, joy, as those are the three things that we're trying to affect, which I think echoes, I don't know, earlier talks I saw. Unlike that other famous triple, fast, cheap, and good, we don't think you have to pick just two. In fact, quality, speed, and joy all feed into each other. If you build the right thing, it will probably be faster than building a buggy mess and having to debug it. if you can build fast, you can iterate and experiment and find your way to the right thing. And we all know that we enjoy building good stuff and building a lot of it. So how much can we really do about quality, speed, and joy? So one simple place to start is just with time savings. We assume there's a certain amount of time every day that people spend just waiting for things to happen, waiting for it to compile. You know, someone else showed the XKCD comic earlier. And that's time that's perhaps not being put to productive use. So if we could just eliminate some of that waiting time, we would boost people's just sheer productivity. So assuming that we have a standard year, 2,000 hours, or a 480-minute day, we can sort of see, like, what does that actually mean? If we want to get a 1% productivity gain, what do we have to do? We got to save about 5 minutes a day for every engineer. So it's not nothing. But if we can find 5 minutes out of every engineer's daily work that they're just waiting for a build or waiting for some test run and shave that out, boom, 1% gain. 10 minutes a day, obviously 2%. And obviously how easy that is to do depends a little bit on how much of a mess your system is to start with. So if it's really messy, there's probably lots of opportunities to get some big time savings. There's also things that happen, it's not every day, save you 5 minutes, but if I can save an extra hour every couple of weeks for each engineer, you know, every so often you go off on a 1 hour debugging session because of a flaky tool, and we can fix that tool so you don't have to do that anymore. That's 1 hour every 12 days is also 1%. Okay, another way we can affect people's effectiveness, and maybe even more dramatically, is, I assume you're all familiar with the concept of flow. Looks like this. Being in the zone when everything's just clicking, you can concentrate, you can solve hard problems. So flow has been studied by psychologists, and I believe it's generally agreed that it takes about 15 minutes to get into that good flow state. So before that, you're just finding your way in, now you're really working. And it takes an instant to get out of it if someone breaks your flow, interrupts you. So modern offices, especially open plan offices, are totally inimical to flow, but that is a talk for another day. What I care about is whether the tools we provide to our engineers are helping to keep people in flow, or worse, those are the things that are breaking people out of flow. So just using that simple time analysis, if I can fix a tool so it doesn't break you out of flow once a day, once a day it breaks you out of flow and I can fix the thing that it does that, that's a 15-minute savings, which is like, if I do it every day, it's 3% gain. But I think flow is even more powerful than that because we're really getting the work done when we're in flow. And so you can have days where you're never in flow. And if, you maybe would have had a half an hour to work before some, pointy-haired boss came and broke you out. But like if your tools did it a couple times in between, you don't get anything done. So that's maybe even more powerful than, 1 or 2%. These might be big changes. And finally, there's something much worse out there, sapping our effectiveness. So we know from Dune, everyone's read Dune, seen Dune, fear is the mind killer. So what does fear look like in software development? Tech debt. Tech debt is the mind killer. So tech debt is lack of quality, it slows us down, it makes us miserable, it breaks our flow, it saps our will to live. It's okay in small doses, just like financial debt, take a little bit on, knowing what you're doing might pay off in the end, but like financial debt, it compounds over time. And a little bit of debt taken on when you're 10 or 100 engineers is gonna kill you when you're 1,000 or 10,000 engineers. And engineering effectiveness teams often have an intimate relationship with tech debt because it often piles up in tooling. Because until you have people whose job it is to build good tools, tools are just a thing that you automate something just to get it out of your face, but you never really make it good because it wouldn't be worth it for just like you or you and your small team. So by the time, especially if you wait a little bit too long, like maybe Twitter did, to really pile in on that problem, you can accumulate a lot of tech debt. And so a team like ours gets really down in the trenches, figuring out how do we get out from under this tech debt? How do we get these 2 mono repi turned into 1 mono repo? How do we get 2 versions of pants on the same thing? And we're still a little bit in the middle of this, but my belief is we're learning some really valuable lessons which will apply to the rest of engineering because there's, tech debt is not limited to us and we can help other teams learn how to get out of it. So I haven't actually gotten here yet, but one of my dreams for EE is to have a team, just a standing Crufts Lane army of like senior engineers who can drop into some code, make it better, and get out of town. And they'd have to be very good, to have other teams be comfortable with that, but that could be huge productivity gains for all of engineering. Someone just comes in and fixes some of those things that you wanted to do but never quite got the time to do. We can help out with best practices. Again, you want to have senior people helping set those, figure out what those are, and spread them through the org and get buy-in, because you don't want to have a bunch of junior engineers like making stuff up for 1,000 other engineers. And finally, quality, speed, and joy. There's a psychological thing about good tools. One is just tools are awesome to work. Like, good tools are fun to work with. They fit your hand, and you can just get your job done, and it's a pleasure. And so I think on that basis alone, we should provide good we should provide good tools for the same reason we provide good food, right? Like, why do we get, so many of us probably work at companies where we get really awesome food every day? It's because it makes work sort of that much more enjoyable. But another thing about tools is that because our tools are software and we build software, if we spend all day building software with other software and it is bad, and we built it and it's bad, then it has this corrosive psychological effect of suggesting maybe we don't know how to build good software. Now, intellectually, like, oh yeah, that tool was built by this team and we're over here building the product and the product's awesome and it's fine, but it's just, it eats away at you. And so I think that's another sort of mind-killing aspect of not having good tools. All right, so I have a little bit of time left and I want to run through a model. Oops, I was already on the model, sorry. That's my model. How long has that been up there? So here's a simple model for the total effectiveness of an engineering org. So E is the total effectiveness. So whatever, some combination, weighted average of quality, speed, and joy. Eng is the total number of engineers you have. EE is the number of EE in my, engineering effectiveness, DevProd, developer efficiency, whatever engineers you're going to devote to that kind of work. So you take the EE engineers out, you have whatever's left, and then you're going to multiply it by 1 for what they would have done anyway. And then the number of EE engineers scaled by this exponent, so this is kind of like big O, right? If S was 2, then that would mean the boost would grow as the square of the number of engineers, which would be awesome. And if you have a company like that, like, can I send you my resume? But if not, it's probably under 1. Like, each new additional E engineer isn't going to add quite as much boost as the last one. And B is just the boost. So based on what we talked about before, I don't know, 2%, 5%, 1%, I don't know, you sort of pick what you think is reasonable. So this is a simple model. Like all models, it is wrong, but it might be useful. And so I've made some graphs, which I'm about to show you, where I've assumed that S is 0.7, so it's not like you don't have to square the number of engineers to get better, but it's definitely sublinear. And B is just 2%. So we're saving 10 minutes a day for every engineer, or the equivalent in joy or quality. So let's look at some graphs. And these, hopefully, I don't know how well you can see that, but basically that's a straight line going down. The x-axis is the number of your engineers that you devote to EE, and the y-axis is sort of the total productivity. And so, yeah, you probably can't read that, but basically, maximum productivity is way at the left, where you devote 0 engineers to tooling. So and this is for a 10-person org. So for 10, don't bother. Like, people will automate their own stuff, but you don't want to devote anyone to it because it just doesn't get you enough. Now we go to a 100-person engineering org. Now you can see the curve starts to bend just a little bit, but not much. So you want to add, given these values of B and S, that's an unfortunate acronym. I didn't think of that. 2 EE engineers, and that will get you a sort of total productivity or efficiency or effectiveness of 101 engineers. So by devoting 2 people to making tooling and everything else better, we're actually getting an extra engineer, essentially for free. Now, come up to 1,000, sort of in Twitter range, and I don't know how many people here work for a 10-person company? Raise your hand. How many people work for 100 or thereabouts, order of magnitude? 1,000, 10,000. Cool. All right, so we've got slides for all of you. So at 1,000, again, you probably can't read that, but it says that arrow is pointing at the maximum, and that's 255 engineers devoted to engineering effectiveness style activities. And that gives you a total effectiveness of equivalent to 1,465 engineers. So not only is the number scaled, it didn't just go from, as we went from 100 to 1,000, it didn't go to 2 to 20, it went from 2 to 255. And the gain we got is disproportionately large as well. Sorry. And now, 10,000, it gets totally off the charts. I don't know if I even believe this, but they're saying here, basically a third of your engineers should be working for Brian O'Sullivan if you're a 10,000 person Facebook-style engineering org. So you can play with these parameters, and I'm too late of time. So let me just say, this is all cool. This model you can quibble with, but there is one caveat, which is in order to get these boosts, you have to standardize, and this is where we get to the pulling out those 999 flowers by the roots. So you can only get these gains if the work that you do affects a large number of people. If you're working on a tool that only 100 engineers use, it doesn't matter that you're in a 1,000 person or 10,000 person organization. So that means we need to standardize certain things, all those elegant, delicate blossoms that grew up during the 1,000 flowers blooming phase that may be very well adapted to their local ecological niche. Nonetheless, you need to pick the ones that are the winners, support the hell out of them so that everybody can get the benefits from all the great tooling you build. And then if you do that, you get to the point where you're ahead of the curve, you're supporting those blessed flowers so well that the only reason anyone would plant any new flowers or any new little volunteer blossoms would spring up is because you're actually not meeting a real need, not just because nothing works, so I'm gonna do it my own way. And when you get to that point, then you actually can sit back and see some team experimenting with a new way of doing things or a new language or a new tool and wait and not be afraid it's gonna overrun your garden, but you can sit back and learn from that and then say, you know what, we're gonna take that in, we're gonna treat that as a flower and we're gonna grow it in as part of our beautiful garden. So with that, I wish you all quality, speed, and joy in your work and a pleasant time tending your gardens.